Okay, welcome to lecture here. We'll get going here on chapter 13 where we left off. Move some stuff around here. Okay, so we've been talking about equilibrium. So last time we talked about Kc and Kp type of expressions. Again, Kc is really the equilibrium constant when you're dealing with concentrations, hence the C on it. And it is the concentration of the products divided by the concentration of the reactants. We do use the coefficients in the balance equation as the exponents for each of the products and the reactants. So it's products over reactants. Um, and when we look at a K value or an equilibrium constant value, it is just a number. So whatever the number is, there's no units associated with it. But the number does help us understand a couple of things that's happening when a system reaches equilibrium. First off, if we do have a large value for K, what that means is when equilibrium is reached, we mainly have products. Again, since you're taking products divided by reactants, in order to get a large value, you have to have more products when it reaches equilibrium. And vice versa, obviously, if we have a small value of K, that means that when we do reach equilibrium, we would mainly expect reactants to be present. What do we consider sort of a large value? And that is the big number of 1. So 1 is considered a large value. Anything basically above 1 is considered large in terms of the equilibrium constant. Anything less than 1 is considered on the small side. Now, we also saw that sometimes we may be looking at not necessarily concentration, but we may be looking at pressures. And typically when we deal with pressures, we could write a equilibrium expression that deals with pressures, and that's what's known as the Kp value, P being for pressure. And we use the partial pressures of our products divided by the partial pressures of our reactants. We do the same thing. We take the coefficients, that's the exponents for each of those, and we divide them out. In most cases, the Kc and the Kp value will not have the same numerical value, but they do tell you the same thing. So again, if you have a small value for Kp, that again is going to mean that you have mainly reactants. If you have a larger value for Kp, that's going to mean you mainly have products. So they do kind of tell you the same thing, even though numerically the values are not the same in each case. We also saw a formula where we can go from one to the other. So if we know the Kp but want the Kc value or vice versa, we could use that equation of the Kp equals the Kc times RT delta N, R being the gas constant, and that is the one we use in the ideal gas law, the 0.08206 version, T being the temperature, which needs to be in Kelvin, and delta N being the change in the moles of gas. So that's products minus reactants. So as we talked about last time, it's important to make sure that you do that conversion sort of correctly. You actually do take the difference between the products minus reactants, because you will get either a positive or a negative number. And obviously that is really important when you put it into that formula that we saw. Otherwise, you'll get a different answer if it's negative versus just a positive number. And we sort of finished up talking about ways that you sometimes will have to manipulate the equilibrium constant for a reaction. So as we talked about in the previous chapter and a couple of times already, not all reactions happen in a sort of one-step process. So sometimes it does happen in multiple steps, and you may have to add together multiple equilibrium type reactions. And if you add together multiple equilibrium type reactions, you could get the overall K value for that by multiplying all the K values together. So if you have two reactions that you add together, each of the reactions have a K value. For the overall reaction, you would actually just multiply the K values together. While some other things that you might have to do in terms of manipulation is you may have to reverse a reaction. So when you reverse a reaction, unlike say something like delta H, when you actually reverse an equilibrium reaction, basically your products become your reactants become your products. So when you actually reverse that reaction, you're actually going to take 1 over the K value to get the new K value. And two other things that you can commonly do is multiply a reaction by a common number. And if you multiply a reaction by a common number, you then would take the K value to that common number. So you would, if you multiply by 2, square, if you multiply by 3, cube it, and so forth. And the last thing that you could sometimes do is divide by a common number. So if you divide something by a common number, you would take the K value to the root of that number. So if you divided by 2 all the way across an equation, you would take the K value and then take the square root of it. If you divide it by 3 all the way across an equation, you take the K value and take the cube root of it. So those are very common ways that you can sort of manipulate equations or reactions and the K values that go with it. And again, that would be a problem where you would sort of be adding multiple reactions together. Lastly, we sort of talked about the idea that when we do see a value for K, it is specific for exactly how that reaction is written. Whatever the reactants, whatever the products, that K value is exactly for that. This is exactly how it's written. And it's for that temperature. So the only thing that really will affect the true value of K is temperature. And what that means is essentially you can, start with different amounts of reactants or products, and it will always come to sort of rest, if you will, at equilibrium with the same proportion of products to reactants. And again, it doesn't matter if you started, say, with 5 of the reactants to begin with, or the next time you started with 2 of the reactants, the equilibrium constant value will remain constant as long as you don't change the temperature. If you do change the temperature, the actual value will change, but then if you keep it at that temperature, it will stay constant at that temperature. So sometimes people miss that part of it where they think, well, I started with different amounts of my reactants, so I should get a different equilibrium constant. And that's really not the case, because remember that really the equilibrium, when it reaches equilibrium, we're talking about the rate of the forward reaction equals the rate of the reverse reaction. So regardless of sort of what you start with or how much you start with, the ratio that you will get at the end will always be consistent and constant. Any questions on that there? And that's basically what this slide says here. You could start at many different sort of positions, but it will always come to the same equilibrium constant when it's all said and done. Any question? Excuse me. Any questions on anything we talked about last time? Okay. So now let's talk about another letter for a second here, and other than K, but the next thing we're going to talk about is what's known as the reaction quotient. And the reaction quotient is basically calculated the exact same way as you would calculate K. So when we calculate Q, we do this exact same calculation. And basically Q is the concentration of our products divided by the concentration of our reactants. So you do the exact same thing as you would do with K. You also would use the coefficients as the exponents, everything pretty much identical to what you would calculate K. So you might be asking yourself, why would we calculate Q, or what is the purpose of Q? The purpose of Q is we typically would calculate Q in a situation where we're not sure if we are at equilibrium. So maybe we're given initial concentrations of everybody, and we can put it in there and calculate Q, and that will help us determine whether or not this system is at equilibrium. And second to that is, if it is not at equilibrium, it will help us decide which way it needs to go to reach equilibrium. So oftentimes we use Q as a way to determine if we're at equilibrium and determine which way we need to actually go to sort of reach equilibrium. And the way we do that is we actually take the Q value and we compare it, excuse me, we compare it to the K value. So if we calculate Q and it is greater than the KC, what that first tells you is the system is not at equilibrium. And in order to reach equilibrium, it needs to go to the reactant side. So if you put Q like they do here on the left-hand side, and you put K here on the right-hand side, it basically goes opposite of the greater than side. So this way would be to the reactants, right? And so if we calculate Q and it's greater than Kc, A is not at equilibrium. And in order to reach equilibrium, we actually need to make some more reactants in this particular case. If you do calculate Q and it does equal K, your system is at equilibrium. And again, what that means is the rate of the forward reaction at that point will equal the rate of the reverse reaction. And lastly here, if you calculate Q and it is less than the Kc, going opposite the way it's pointing, would take you to products. So A would mean it is not at equilibrium, and B, what it would mean is you need to make more products to reach equilibrium. So there's really kind of two places we'll see Q pop up in a number of spots, but sort of in this chapter, there will be really a question that's just a basic Q type problem. Like the question will ask, here's all the reactants and products concentrations, is this system at equilibrium? And in that case, you basically just plug it into the Q expression, compare it to the K value, and determine if it's at equilibrium. Another place that we will see it is later on in the chapter when we start doing ice tables and stuff like that. Sometimes it's important to calculate Q to make sure that you're not at equilibrium. And if you're not at equilibrium, important to know which way you need to go to reach equilibrium. So later on, we'll kind of see that as well. Clearly, in order to calculate Q, since it is calculated the exact same way as K, you need to be given the concentrations of everybody. So you need to be given the reactants, the products, and those type of things. So because you are sort of given the amounts of reactants and products, it would imply that this reaction probably has taken place. And that is really why we're calculating Q, to determine, are we at a point of equilibrium? Are we just kind of starting the reaction? We haven't reached equilibrium. And again, that's sort of the main idea here. So calculated the exact same way, products over reactants, coefficients as the exponents. So why don't you give one a go here and see what you come up with. So if we start this reaction with 0.249 moles of N2 and 3.21 times 10 to the minus 2 moles of H2 and our NH3 in a 3.5 liter vessel, and the Kc is 1.2, is this system at equilibrium? And if it is not at equilibrium, which way does it need to go to reach equilibrium? So why don't you take a couple minutes here and work that out. Okay, so let's take a look here. So we're given really we got the moles of everybody. We also have the liters. So really from the moles and the liters, we could get the molarity. So we do have the concentrations pretty much of everybody given to us. We also obviously have the K value given to us. So this is your kind of classic, straightforward Q type problem. So again, to calculate Q, it is done the exact same way as the equilibrium constant. So in this case, Q would equal the concentration of NH3. And again, we would square it because of the coefficient. We would divide it by the concentration of N2 and our H2, that would be cubed in this case. So the first thing we want to do is, since we do need the concentration, we should probably figure out the molarity of everybody that's going on there. And if we do that, let's take a look here. So the concentration of N2 would be the moles, which is 0.249, divided by the liters, which is 3.5. And that would give us something like 0.0711. We do the same thing for our H2. It had 0.0321 moles divided by 3.5 liters, and that equals 0.00917 molar. And lastly, our NH3 was 0.000642 divided by 3.5 liters, 0.000183 molar. So that's just calculating moles like you've done hopefully a number of times at this point. So Q would equal NH3 squared, our N2, and our H2 cubed. So we want to put these guys in the right spots. So we're going to take 0.000183. Again, we're going to square it, divided by our N2 concentration, which was 0.0711, and our H2, which was 0.00917. And again, we don't want to forget to cube that number. And it looks like if you do all that, you end up with 0.611 for the Q value. So if we remember from the problem, our K value is 1.2. So in this case, Q is less than K. And what that tells you is, first off, you are not at equilibrium. And in order to reach equilibrium, going opposite of where that sign is pointed, you need to go to your products. So the reaction needs to go to the right to form more products to reach equilibrium. Any questions on that there? What I do is basically a table where we have ICE in it. And what each of these sort of mean is the I is the initial concentration, the C is the change, and the E is equilibrium. So when we do these, we typically, for a lot of things, would like to do ICE tables in molarity. So we start with our initial concentrations and we do a change. So say we had an equation like 2A plus 3B goes to 2C or something of that nature. And let's just say that the initial concentration of A was given to us as 4 molar. Initial concentration of B was given to us as 2 molar, and that was all that was given to us. So if that is all that's given to you, which is the reactant side, you could probably safely assume that the product side is 0 to start with. So a lot of times you'll just be given the initial concentrations of your reactants. Again, you can assume that on your product side, you got 0 happening. You could also then safely probably assume that if you're not given anything in terms of the products, that the reaction is heading towards the right-hand side or towards the product side. And that's going to be important for the change part of the ICE table. The change part is usually we use a letter to represent the change. So usually we use X as the letter to represent the change. And when we do, since it is assumed to go from reactants to products, the amount of reactants should start to be decreasing here with time. And that means that we would represent that with a minus on our reactant side. But in addition to the change, which is X, we do have to do something like minus 2X here. And the 2 is because of the coefficient here in the balanced equation. That 2 that we put down here with the 2X will take care of all the mole to mole relationship, the stoichiometry of the equation. So it's really important that you put the 2 here in this particular example. Again, if you don't do that, you will not be taking into account the mole to mole relationship, and you will not get obviously the right answer when it's all said and done. We will also have minus 3x in this example, again, because of the 3 that is here. You do need it there as well to take into account. And on our product side, we will have plus 2x, plus because as this reaction is going to the products, we should be increasing the amount of products. And that means that we represent that with a plus sign. Also, same thing here. We have a 2 because of the coefficient. And when we get to equilibrium, what we're going to do is just basically bring everybody down. This would be 4 minus 2x. This would be 2 minus 3x. And this would be 2x. So this is the basic way that an ICE table kind of looks like. We do our initial concentrations. We use X to represent the change. And again, if it is proceeding from reactants to products, our reactant sign would be minus and our product side would be positive. And then we carry it down. So the question is, what do we do now? So the goal at this point really is to solve for X. And we want to solve for X. And the way we do that is we would actually use the equilibrium expression to help us. So in this case, C would be squared, A would be squared, and B would be cubed. And at this point, they would probably give you the equilibrium constant value. So you would have that. And what you would do at this point is basically substitute in your equilibrium part. And basically, you'll do some fun math here and solve for X. When you do solve for X, that X will equal the X that's here. That X will equal the X that's here. And that X will equal the X that's here. So once you solve for X, you'll be able to really determine the value of the equilibrium concentrations for everybody by putting it in there. To solve for X, there's multiple ways you could solve for X. Sometimes you may have to do something like the quadratic formula. Sometimes you may not need to do that. So there's a lot of different math ways that you can solve for X, and we'll talk about or see some here in some of these examples. Question on sort of your basic ICE table setup. So earlier, when I was talking about Q and we were talking about Q, that I said there's another spot where Q will sometimes come into play, and that is in this situation. In this situation, we can safely assume that this reaction is heading to the product side because we were not given any products to start with. The 155 I just made up. So that would be the equilibrium constant. In a problem like this, you would be given the equilibrium constant value. So it's just made up as sort of an example. Now, in a problem where you are actually given, say, a value for this guy, say you were given 3 molar here, what that would mean is you're not 100% sure that this reaction is actually going to head this way. Maybe it's going to head this way to reach equilibrium. And this would be the second place where you would want to calculate Q. So if you're given sort of an equilibrium problem like this, where you have the starting amounts of everybody, it is a good idea to calculate Q first, and just to make sure that it is actually heading in this direction towards the product side. If it wasn't heading towards the product side and it was actually heading the opposite way towards the reactant side, what that would affect is it actually would be going in this direction, which means this guy would be negative and these guys would be positive. So that is the second place where it occurs, kind of less common, but it does happen. So again, a recommendation is if you are given starting amounts of everybody, you should calculate Q to verify which way it's heading because it can affect the change part. Probably 9 times out of 10, you could probably blindly, even probably more than that, 9.9 times out of 10, you could blindly just go this way, minuses on the left and positives on the right. But there is an occasional chance it could actually be going the other way. Question on that. All right, let us then, and that's basically what it says with all the writing underneath there, what we just talked about. Let us actually go through one here together so that you get an idea as to sort of the steps that you should follow here. All right, so we have this problem here, and we have a reaction of Br2 to 2Br, and the equilibrium constant is 7. So again, they typically give you it. If the initial concentration of Br2 is 0.663, calculate the concentration of everybody at equilibrium. So let us go through this together. So the first thing you want to do really is you can start with your ice table. So we have Br2 going to 2Br. So initially, we are only given the concentration of the Br2, which is 0.663. And again, in this case, if you're only given the initial concentration of your reactants, it is pretty safe to assume that your products will be 0. So again, pretty safe assumption there. Also means since we were not given any products, it is also probably a pretty safe assumption that this reaction is heading towards the right in this case. And that's important for our change part. So our change part here will be minus x, coefficient is 1. And again, on our product side, plus, because it should be increasing, 2x. And again, the 2 for the coefficient that is there. That's going to give us at the end here 0.663 minus x and 2x. First off, any questions on the ice table? So now when we look at it, we can write our equilibrium expression. Our K would equal the concentration of Br squared divided by Br2, and that will equal 7. So what we're going to do is basically take our equilibrium values and pop it into our expression here. So when we do that, we're going to get that 2x, which is our product, squared, divided by 0.663 minus x is equal to 7. At this point, what we want to do is mathematically here solve for x. And to do that, basically what we're going to do is we can square the top here. And when we square the top, we want to make sure that we do the number as well. Can't tell you how many people will write 2x squared there and forget to actually square the 2. I'm then going to multiply what's on the bottom to the other side. So I'm going to multiply everything on the bottom to the other side. And when I do that, I will get 4.641 minus 7x in this particular case. Now, I'll switch the page here. Putting everybody together on sort of one side gives me 4x squared plus 7x minus 4.641 equals 0. Perhaps you recognize this as like the quadratic formula type of equation. where we have ax squared plus bx plus c equals 0. And that goes with our good friend, which you'll be very familiar with in this class, quadratic formula of x is equal to minus b plus or minus the square root of b squared minus 4ac divided by 2a. So obviously this is a, this is b, and this whole thing with the negative is c. And that's what we're going to put into here. So if you're familiar with the quadratic formula, you know that you actually do get two different answers when you go do this. So let's just kind of put some numbers in and see what we get here. Excuse me. So that means that x will equal minus b, which in this case is minus 7, plus or minus the square root. And what I'm going to do is I'm going to clean up all the numbers inside. So I'm going to take my b and square it, which is 7 squared. I'm going to minus it from 4 times a, which is 4, times c, which is minus 4.641. And that gives you about 123.256 if you clean up the inside. And if you take the square root of that while we're here, maybe gives you something like 11.10. That's going to be divided by 2 times a. So a is 4, and 2 times 4 is 8. So again, I just kind of put in all the numbers for the square root and just kind of got a number there. And in this case, we have two answers it's going to be. So the first one would be minus 7 plus 11.10 divided by 8. So if you do that, minus 7 plus 11.10 divided by 8 gives you an x value of 0.513. The other value will be minus 7 minus 11.10 divided by 8 gives you 2.2 minus 2.263. And these are our two values of x that we can get from solving this quadratic formula. First off, any questions on the math part of it? Okay. Now, when you do solve for this, one of the numbers will not make sense. And in this particular case, if we go back to our ICE table, and if I look just at this number, for example, and if I put in there the x value that is negative, it is going to give me a negative concentration. And I cannot have a negative concentration. So when you solve the quadratic formula in these type of problems, one of the answers that you go to put back in will not make sense. And in this case, the one that's negative will not make sense because, again, you cannot have a negative concentration. That means that this value here should be my correct x value. And what we want to do is go back to our ICE table. And we want to go back to our equilibrium line, which in this case was 0.663 minus x and 2x. And we want to plug this value into both of those values. So if we did that for our BR2, that would mean that we would have 0.663 minus 0.513, which would give us a value for BR2 at equilibrium of 0.663 minus 0.513. And of course, come here, calculator. Don't die so quickly. 0.663 minus 0.513. There we go. Gives us a BR2 value of 0.15 molar, as it is a concentration. And for our BR concentration, it is equal to 2 times x, which means 2 times 0.513. And if we do that, what we will end up with is 2 times 0.513, 1.026 molar would be the concentration at equilibrium of our Br, and 0.150 would be the concentration of our Br2. Question on that calculation there? One of the nice things about this is it is math, which means usually in math, there is a way you could kind of make sure everything makes sense. And because this is math and we already know that the equilibrium constant is Br squared divided by Br2, and we already know that that value equals 7, if I now take my equilibrium concentrations and put it in here, 1.026 squared divided by 0.150, I should get about 7, which I do. So that's a good way you could actually check yourself at the end. Once you determine those equilibrium concentrations, you could put them into the equilibrium expression, and you should get pretty much the same value you got for the equilibrium constant. May not be perfectly equal, but it should be pretty darn close with some rounding, but it should be in the same ballpark. And if you do have time, it's probably a good idea to do that, because there is a lot of places where the math could go really bad for you and a lot of people. So if you do have time, you could check it. And if you see that, hey, my equilibrium constant was 7, and with my equilibrium concentrations, my equilibrium constant is like 127, something probably went wrong there in terms of the calculation. Any questions on any of those sort of steps there? All right, why don't you try one then and see? So why don't you give this one a go? We have a mixture of 0.5 moles of H2 and 0.5 moles of I2. We're placed in a 1 liter flask. The K value is 54.3. What is the concentration of everybody at equilibrium? So take some minutes here and give it a go, see what you come up with. let's take a look and kind of see how we're doing. So in this case, we have some H2, we got some I2, and it's in a 1 liter flask. And we want to know what is the equilibrium concentrations of everybody. So we are given enough information here about H2 and I2. We're not given anything about this guy. So again, we could probably assume that this reaction is going to head in this direction. If we do our equilibrium expression for it, our Kc will be the Hi concentration. And again, we need to square it because of the coefficient. We want to divide it by our H2 and our I2. And in this particular case, it equals 54.3, which was given to us. So obviously, we do need the concentrations of everybody. So this one's not too hard. Since H2, we got 0.5 moles, and the total volume was 1 liter. That gives us 0.5 molar. And our I2 was the same in this case. So our I2 would also be zero point 0.5 moles divided by 1 liter equals 0.5 molar. Any questions on that so far? So just like we been talking about, we want to find equilibrium concentration. So it is going to require an ice table, which is pretty much every calculation that we do here. So here we have our equations. So initially here, we do have 0.5. We have 0.5. And again, nothing given to us. So safe to assume that that's going to be 0. Again, also safe to assume that this reaction is probably heading in this direction. And that's important for the change part. That means that we should have minus x as our reactants should be decreasing. Minus x, again, the coefficients are 1s here. On our product side should be increasing, so that's going to be plus 2x again for the coefficient there for the stoichiometry. And that means that at equilibrium, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table, where all the numbers came from, or any of those things? Okay, so just like we've been doing, what we're going to now do is take the equilibrium line and put it into our expression. So again, K in this case is our Hi squared, our H2 and our I2. And putting that in gets us that we have 2x squared divided by 0.5 minus x, 0.5 minus x, and that is going to equal 54.3, it looks like. At this point, we do want to solve for x, so you could factor and FOIL and all that good stuff. But as you will hopefully quickly learn, if there's a better way, you should probably take it. And if you did not recognize it or do not recognize it, this is actually a perfect square. So you can actually just take the square root of both sides here, and you'll be fine. And if you take square root of both sides on the left, we get 2x up on top. We get a 0.5 minus x there. And the thing I always forget to do, actually square root the other side there. So the square root of 54.3 should give us something like 7.3689. At this point, we now want to solve for x. So we're going to multiply this to the other side. And that's going to give us 2x is equal to 3.6844 minus 7.3689x. Going to combine the x's to the other side. That's going to give me 9.3689x is equal to 3.6844. I'm going to divide that to the other side. And if I do all that good math, I end up with an x value of 0.393 in this particular case. Question on that part of it there. Again, you could go the long way in terms of solving it. You should hopefully end up coming out with the same answer pretty much. Maybe like slightly different with rounding, but should kind of get there. That x, as we talked about earlier, is going to be every single x here on our equilibrium line. That means that the concentration of H2 will equal the concentration of I2, and that would be 0.5 minus 0.393, and that would get us 0.107. And the concentration of our HI in this case would equal 2 times x, which would be 2 times 0.393. And that would get us 2 times 0.393, 0.786. And those would be the equilibrium concentrations. And like I mentioned before, if you want to check yourself, you could do that by putting it back into here. And that would give you 0.786 squared divided by 0.107, 0.107. And again, if we did everything correct, it should equal pretty close to our equilibrium constant value. Again, maybe slightly different with rounding, but should definitely be in the same ballpark. And if you did that, you do get something like almost 54, 53.96. Get about 54, which is a good way to, again, sort of check yourself. So this is a nice example because it demonstrates the point that you don't necessarily have to use the quadratic formula. If there's a better way to do it, you can. And for time saving, I would recommend it, but sometimes you do have to use a quadratic. Question on any part of that, where any of the numbers came from, why I got any of those. All right. If you are professionals, then why don't you give the next one a go here and see what you come up with. We're using the same equation and also the same equilibrium, just some different concentrations. Looking for the same thing. We're looking for the equilibrium concentrations of everybody. So see what you come up with on this one. Okay, so let's take a look and see how we're doing. This one's a little bit longer of a one, I think, but hopefully you're making some good progress, getting towards the end, so you can kind of see how you're doing here. So in this case, it's a little bit different, even though it's sort of the same reaction, same K value and everything. In this case, we are given the concentrations of everybody. So we have the H2 concentration, the I2 concentration, and the HI concentration, and we're given the equilibrium constant. So this is a place where we've been talking about that you probably do want to perhaps calculate Q first, just to verify you're not at equilibrium, which I would imagine you're not. Otherwise, this is not a great problem. But more importantly, to just verify that you are going from reactants to products. So probably in this situation, again, you can calculate Q because they did give you all of the starting amounts. And again, this is going to help us verify that it's not at equilibrium, which, like I said before, I wouldn't think it is, but it'll also verify which way it needs to go to reach equilibrium. So if we pop in our numbers here, we get 0.0224 squared. We also get 0.00623 and 0.00414. So if we calculate Q here, we will end up with looks like 19.5 as our Q value. Again, we could compare that to our K value, and in this case, Q is less than K. So that does tell us that we're not at equilibrium, which we probably could have guessed because of the type of problem. But more importantly, it tells us to reach equilibrium, we do need to proceed in this direction towards the products, which means that our change part should be okay because we should be heading minus on our reactants and positive on our products. So again, this is sort of the other place where Q could sort of creep into where you probably should calculate it again in sort of a non-Q problem to verify that you're not at equilibrium and which way you need to go to reach equilibrium. Like I said before, if you maybe missed this part or didn't do this part, probably 9.9 times out of 10 you are heading towards the products. You'll probably be okay in most of the calculations you do. But again, it is possible it could be heading in the opposite direction. Any questions on that part of it there? So now that we do have it all worked out that it is not at equilibrium and it is going to be heading, heading towards our products, we could start the actual problem here. So we have our H2 plus our I2 going to our 2HI, with our K being the same as our Q in terms of the expression, products over reactants. And put it in our initial concentrations of everybody. This looks like 0.00623, 0.00414, and 0.0224. Change here, now that we did verify it's going towards products, going to be minus x, and plus 2x again for the coefficient, which means when we are all said and done here, 0.00623 minus x, 0.00414 minus x, and 0.0224 plus 2x. So plus here, so that's important. At this point, we're going to put all these guys into our expression. And if we do that, we will get 0.0224 plus 2x. We do need to square it. We're going to divide it by 0.00623 minus x and 0.0414 minus x. And all that good stuff there is going to equal 54.3. Any questions so far on the ice table, putting it into our expression, any of those things? So the bad news here is this is not a perfect square, so you cannot just square root both sides. You do have to do some fun math here, distribute, FOIL, whatever you're going to do with it, the top and the bottom here. So I will just maybe write it like this, and we'll go through that part there so you can see the math, and we'll hope for the best here, didn't mess anything up. So basically, this is the same as two of these, right? All right, so obviously you need to kind of foil both sides and all that good stuff. So let me do the top one first there. So we're going to take 0.0224 and times it by 0.0224. And that is going to give me 0.000502. That is going to be plus 2 times 0.0224. That's going to be 0.0448x plus the same thing, 0.0448x, and that's going to be plus 4x squared. So that is just factoring out the top guy there. Again, foiling it or whatever you call that, factoring, whatever they call that these days. I'm now going to just kind of clean up everything here for the top guy. That's going to give me 4x squared. I'm going to add these two x's together, and that's going to give me 0.0448 plus 0.0448. Going to give me 0.0896x plus 0.000502. That is, I'm just going to put top next to it. So that takes care of the top part. We're now going to do the same thing here for the bottom. So let me factor out the bottom the same way. And I'll slap a different color there. So I'm just going to do the bottom part now. So again, I'm going to multiply everybody, across and kind of combine. So that's going to give me 0.00623 times 0.00414. I didn't lose anything along the way. That's going to give me 0.0000258. That's 4 zeros, right? Yep. And that is going to then be minus 0.00623x minus 0.00414x, and that will give me plus x squared. Again, here I'm just going to kind of clean up the bottom part, and that should give me x squared minus 0.00623 plus 0.00414 minus 0.01037x plus 0.000258. So this is my bottom part of that. Any questions on that so far? So what I got going is, let's go with real quick here. I got 4x squared 0.0896 and 0.000502 on top divided by the bottom there, if I didn't mess anything up there, x squared minus 0.0103, so we got x squared minus 0.01037x, and on the bottom there 0.000400258. All right, And that is still equal to 54.3 on the other side. I am then going to multiply the entire bottom to this side here. And if I do that, that is going to give me something. That will give me, on the left-hand side, we will be left with 4x squared plus 0.0896x plus 0.000502 equals 54.3x squared minus 54.3 there 0.01037 54.3 times 0.000258. That's going to give me 0.00140. At this point, we're going to bring everybody hopefully to one side. So usually we take the x squared and leave it positive. So basically I'm going to bring everybody from this side to the right-hand side. And when I do that, that gives me 50.3x squared, 0.563 plus 0.0896 gives me 0.653 x, and lastly 0.00140 minus 0.000502 gives me something like, I'll just kind of clean it up in scientific notation here, 8.98 times 10 to the minus 4 equals 0. Any questions on that math? That is the step-by-step math of it there. You would feel like you've already done the problem at this point, but now you could actually do the problem because now we get to go into our quadratic here that we have our A, our B, and our C happening here. And if we do that, that means X is equal to minus B, which in this case would be 0.653, plus or minus the square root. Again, I'm just going to put the numbers in and kind of clean it up. So that is B squared, which would be 0.653 squared minus 4 times A, which would be 50.3 times C, which would be 8.98 to the minus 4. Looks like you get something in the square root there of 0.2457. Taking the square root of it gets you something like 0.496, all divided by 2 times A, 2 times 50.3, 100.6 on the bottom. At this point, again, going to give us two values for our x's. Again, one based on doing the plus and one based on doing the minus. And if we do the plus, we're going to take 0.653 plus 0.496 divided by 106. That is going to give us an x value of 0.0114. If we do the subtraction, 0.653 minus 0.496 divided by 100.6 gives us an x value of 0.00156, I believe, in this case. So those are our two x values. Again, in this case, our x values are actually both positive. So one of these answers will not make sense. So let us go back to our table here where it's at. So this is our ICE table. And if we look at our H2 concentration, or even our I2 concentration, we will see that the value of 0.0114 is too big. It's going to give us a negative number when we put it back in there. So this value here that we got is going to be too big. Will give us a negative number, not so good. So that means that the correct x value that we need is right here at the 0.00156. And now we could actually solve for everybody's concentration there. And if I do, let's see what we got. We got for our H2, it would equal our initial 0.00623 minus 0.00156. And that would get us 00623 minus 0.00156 gets us a concentration of 0.00467 molar. For our I2, it will equal 0.00414 minus our x value, 0.00156. And that's going to give us 0.00414 minus 0.00156, 0.00258. And lastly, for our, what I'm going to do is maybe clear it up something so it could have a spot here to write. Just kind of clear that guy up. And lastly, for our HI concentration, it is going to be our initial, which was 0.0224 plus 2x. So that's going to be 0.0224 plus 2 times our x value of 0.00156. And that will get us 0.0224 plus 2 times 0.00156 gets us 0.0255 as our equilibrium concentration of our product. And again, if you take those numbers and you substitute it back into your equilibrium expression, you should get, again, pretty close to our 54 number. And if you do, you get about 54.1-ish or somewhere in that ballpark, or 54.0, and it is good. Question on any of these steps here. So obviously, as you can see, there is a lot of places where the math could go really bad for you. You want to make sure that you go at it slow but efficient. And most importantly, where I see people mess up is extra zeros, copying it over, not correct, minuses where they should be pluses. So again, you just gonna want to kind of do it step by step, even like I did there, where I just kind of took the top part, did the top part, then did the bottom part, then put them together. Sometimes that's better than trying to do everybody together, because again, there's a lot of places where you could just be off by something, forget a zero, miss something, and it will obviously throw off all your numbers.
I had a question for when you're plugging it into the quadratic formula.
Yeah.
For the B, 0.653x, would you bring the negative with it?
You do, yeah. So you do bring in the negative. So the reason I didn't bring the negative on the outside there was because the formula is minus b. So that's how come the minus b became, 0.653 plus or minus, and it would be minus 0.653 squared. Just like, for example, if c was negative, you would take that negative in with it as well. So you do take the negative into the quadratic.
Thank you.
You're welcome. Other questions? So kind of like the previous one we did, I think, if I'm not mistaken, where are we at there? Like on this particular one here, I think, where are we at there? That was the perfect square, the one previous to that, I think. There we go, yeah. like on this one here, when we took this C in, we did keep the negative with it as well. So you do want to keep the negatives when you do put it into the quadratic again. Otherwise, obviously, you'll get the wrong answer. Other questions on that? All right, so this is funness, isn't it? It's good times, good math, lots of paper, lots of scratching out things. All right, we will stop there, and obviously we'll continue on doing another example or so next time, another type of equilibrium problem. So today for lab, we're off to the next experiment, which is kinetics activity, I believe. So we'll talk about that experiment and you'll go work on it. So I'll see everybody about 11:30 in the lab meeting. If you didn't type here the first time, please type here now, and I'll see everybody in about 20 minutes or so.